Okay, so today we're going to talk about MIPS instruction decoding. And so as you can see, the instruction decoder circuit is at the bottom down here, and it generates a whole bunch of signals. To avoid cluttering this diagram, they haven't drawn the wires connecting these signals to the things that they control, and instead they've just labeled them with their names. So for example, this multiplexer over here is controlled by the mem-read signal, which is this bottom one generated down here. And so I'm going to talk about a way to build instruction decoders that I personally think is particularly easy. It's not NAND-efficient, so if you care about Turing complete score, this is not the way to do it. And also, a lot of the time, you can design your instruction set to make decoding easier in particular ways. For example, by making certain bit patterns always have the same meaning, then you don't need to decode the entire instruction. MIPS doesn't quite work that way for a lot of sort of complicated reasons. There are some bits that do always mean the same thing in certain cases, but picking them out is pretty tricky and takes a lot of circuitry, so while you might want to do that in the real world, it's pretty hard. I don't want to focus on that here. You can feel free to do something more involved if you like, as long as your decoder generates the same truth table, your MIPS machine should still work. So yes, the goal here is to build this thing down here. And I may put the truth table in a paste bin. I have it written out for myself. I'm probably going to be looking at it while working on this. I made a version of it already, but it was with the smaller component factory, and it was very packed for space, so I don't think it's worth looking at that one. Unfortunately, we're just going to do it over from scratch, and since we have a lot more space now, I have a pretty good idea for routing that should help us keep it neat. The one thing that I do want to do is I want to talk about which order we should put these signals in, right? Because when you make a decoder, it's not just generating these signals. It's generating these signals in a way that lets you lay out the rest of the machine cleanly. So if we want to try to stick with this layout, we can set up the decoder so that it outputs all the control signals along the top, and we just want the control signals to be vaguely left to right, sort of as much as possible. So we can see we need read source, write enable, something called LUI, and this isn't really read, it's a register destination. I just pronounce it read because it looks similar. We have ALU source, so that controls the second argument to the ALU, whether it's the immediate value from the instruction, if there is one, the immediate value but sign extended, and we'll talk more about what sign extending means in the next part, I think. Or if it's the value coming out of the B register, by which I mean the register that the B address points to. Of course, there is no single register named B register. Then we have the ALU operation, this mem-read control, this set less than control, SLT, word write enable, and byte write enable, and then byte load. And this multiplexer is not controlled by a control signal, it's controlled by the bottom 2 bits of the address. So let's just plan to put the pins in the order that I just said, and I'm sort of doing this part live, so I'm going to write that down now. So we're going to do RD source, LUI, write enable, then control type, then ALU source, and it's called ALU source 2 in the diagram because it's the second argument of the ALU. Then we have ALU op, then we have mem-read, set less than, word write enable, word write enable, byte write enable, and byte load. And then we're also going to need one extra control signal called signed. And the reason that we need that extra one is because we're going to implement a couple more instructions than this data path implements. In particular, we're going to implement both signed and unsigned less than comparisons. And we're also going to implement load byte and load byte unsigned, one of which does sign extension, and again, we'll talk about that later. And we need this flag to control which one of those things we're doing. So for now, I'm just going to plan on putting that signed value all the way on the right. I think that's probably a good place for it because its control is needed over here on this wire to the right of the byte load multiplexer. It's also needed up here, but that's fine. We can just run the wire across. So anyway, as we build the decoder, try and keep this diagram in mind. Think about what these different control signals are doing, and if you want to like pause the video and look at this data path for a while and try and understand it, that can be a good idea. Because really, it's hard to build an instruction decoder if you can't visualize what these signals are controlling. But if I talk about every control signal for every instruction that we implement, this video is going to take like 3 hours, and I don't really think anyone wants that. So yeah, so I think let's just jump straight into building the thing. Oops. So I have a big component space open in Turing Complete over here. This is on the dev branch, so I have big components available. Unfortunately, the text at the bottom is sort of hard to read at the moment. Hopefully that'll be fixed soon. This component is currently labeled MIPS decoder. So, if you remember from the instruction layout, which we talked about in part 1, in fact, I can actually pull that back up. That probably would have been a good idea. Over here, down at the bottom, you can see that the top 6 bits, bits 31 to 26, are always the opcode. And then for R-type instructions, there's another field at the bottom here called funct. And these two fields control which operation we're doing. So the instruction decoder just takes those two fields as input, and we'll split them off from the rest of the instructions somewhere else, not inside the instruction decoder. So the only inputs that the instruction decoder needs are the opcode and funct. And one notation that you can use if you like specifying how many bits are coming in when it's not all 8 of them, you can do this over 6 thing, which means 6 bits coming in over there. I'm not sure I centered that very well. Nope, I think I got lucky. I think it's perfect. Okay. So like I said, I'm not going to focus on a very NAND-efficient way to do this because I don't think that's worth very much. So instead we're going to basically match exactly the values that we care about to identify different instructions. The way that we're going to do that is we're going to just literally take these byte equals components. For example, I'll put one up here, and attach a byte constant with the value of the instruction that we're looking for. So say we're looking for, I don't know, the jump instruction, which is just called J. Its opcode value is 2, so we would put a byte constant here with the value 2, and connect it to this equals, and then we're going to also run a wire like this, which will be connected to the opcode, like that. And so this way, we can identify all of the instructions super easily. So this is J, and we're just going to keep doing that. And so I'm not going to cut this out. I'm going to do this one by one, because this way, as I do these, I can talk about all of the instructions that we're going to implement, because one page of the green sheet doesn't have all of them, and the other page of the green sheet has too many. So the jump instruction is just direct transfer of control, jump to the address identified by the instruction. The next one is called jump and link, JAL. Its opcode is 3, and what it does is it jumps to the address specified by the instruction. It's also a J-type instruction. But it writes the value of the next instruction in sequence, so the instruction that would have been executed if we hadn't performed the jump. It writes it to register number 31, which is also called the return address register. So JAL is used for function calls. This is sort of like the call instruction. You'll notice that I didn't say it pushes anything on the stack. MIPS doesn't have a hardware stack like leg does, and there's no explicit push and pop operation. If you want to stack, you have to do it in RAM. And once we have the full machine, I will show some examples of how to do that. So the next instruction is called BEQ. Its opcode is 4. They're going to stop going so densely in order like this pretty soon. That noise was on my end. Apologies. So BEQ stands for branch if equal, and it's basically a conditional transfer of control. It doesn't jump directly to an address specified in the instruction. Instead, the instruction specifies an offset from the next instruction, and that offset is added to the address of the next instruction, and control is transferred there. And there are good reasons that you might want to do it that way. If you're interested in that, I suggest you look it up, because again, that's another thing that I just don't have time to talk about why you want to do things this way in this video. If people are really interested, I can make another video talking specifically about MIPS design decisions, of course. Then this next instruction with opcode 5 is BNE, branch not equal. This is just another conditional branch instruction. It's exactly the same, except that the condition is inverted, right? You branch if the two arguments are not equal instead of if they are equal. The next instruction has opcode 8, and its name is add I. So whenever there's an I on the end of an instruction name, it means immediate, and I'm just going to do the rest of these wires later, because I can do them with copy and paste really quickly. So this takes one argument from... Why is that a byte wire? Oh, it's not. It's just brighter for some reason. Okay. This takes one argument from a register, from the register addressed by the A line, and it takes the other argument directly from the immediate fields. This is an I-type instruction, and in fact, branch equal and branch not equal are I-type instructions as well. The next instruction has opcode 9, and it is called add IU. And in fact, now that we've sort of got this this pattern going down, I can just copy and paste this section, like that, and I can just replicate this a bunch of times. So add IU is exactly like add, and I actually talked about the difference between them in the first video, so you can go back to that one if you need a refresher, but essentially one of them is intended for signed arguments and one of them for unsigned arguments. We don't particularly care about the signed flag for add IU because, or rather for add I, which is the signed one, because it's not going to control anything for that instruction. Okay. So the next one after add IU is set less than, or wait, sorry, is something wrong here? Add IU is 9, that's correct. Yeah, so the next one after add IU is set less than immediate. So again, just an immediate mode instruction, and there will be non-immediate versions of all of these things. And the one after that is, of course, set less than immediate unsigned, SLTIU, and its opcode is 11. Okay. The next one is going to be opcode 12, which is and I. So that's logical and with an immediate. The one after that is going to be or I, which is logical or with an immediate. Then XOR I, which is of course logical XOR with an immediate. And these just have increasing numbers. That one's 13, this one's 14. You may remember from the first video that there's another logical operation, NOR, but it doesn't have an immediate version for some reason, so we're not going to implement it. The next instruction is called LUI, which is short for load upper immediate. Now, of course, since the I-type instructions, the immediate type instructions, they only have 16 bits for the immediate, but MIPS has a word size of 32. So if you want to put a whole word in the immediate, you can't do that. So instead, if you want to load an immediate that doesn't fit into 16 bits into a register, you first use LUI to load the top 16 bits, and then you use OR-I to basically tag in the bottom 16 bits. So you do it in 2 instructions instead of 1. And that follows the sort of general RISC idea of make the common cases faster. So the common case of an immediate value that does fit into 16 bits is much faster. And because of the way that MIPS works, that case also encompasses signed numbers, where you need the top 16 bits to be all ones. That's what sign extension is for, and like I said, we'll talk about that more later. So anyway, LUI's opcode is 15. This is load byte. It reads a single byte from the memory, and the memory is byte addressable, so this can be any byte. Its opcode is 32. This one is load word. Now, even though the memory is byte addressable, opcode 35, even though the memory is byte addressable, the address for a load word instruction must be byte aligned. The other thing is that all 5 of these are memory operations. They don't take their address directly from a register. Instead, they use what are called offset addressing or indexed addressing, where they take a base value from one register, but then they also have an immediate value, which is added to that base value to produce the actual address. For load word and store word, the resulting address has to be word aligned, which means it has to be a multiple of 4. But for load byte unsigned, and store byte, that is not the case. So the next instruction is load byte unsigned. Its opcode is 36, like that. Then store byte, its opcode is 40. Nope, I do want that one. There we go. And then the last one is store word, and its opcode is 43. Like that. Okay. So now I can just take this whole thing and move it down slightly, and I'm going to move it a little bit further than it looks like I need to, because the next group of them doesn't have as many instructions. And now I can take this, actually, yeah, I won't be able to do it if I also grab the byte constant. So yeah, I can take this wire, and I can just, there we go. Not sure why it's so far away from my cursor. Clean up that mistake in a moment. And I can just connect all of these equals to the pins. And so now we can identify exactly which instruction we're looking at for the instructions that have actual opcode values, which is not all of them. So in order to identify an R-type instruction, you can look at the opcode and notice that the opcode is 0. And if the opcode is 0, it means you definitely have an R-type instruction. You need to look at the funct field instead. So actually, I'm going to give myself a little bit more space than this. Let's do it like this. So the thing is, we don't want to have to like multiplex between these signals because there's so many of them. So instead, I used a little trick for this part, which is, since we know that there's only 6 bits coming in on this input wire over here, it says over 6, what we can do is we can detect if the opcode is 0 using a custom component like this one. The output pin is just on if the input is 0. So you can see it'll stay on, but now if I change the opcode to anything, it'll turn off. And we can put this in the 7th bit, because we know that the funct only has 6 bits, so this bit will never be on. And in fact, we didn't want 0, we wanted not 0. And so now, if the opcode is in fact 0, well, actually, I guess we should put in this step first. So first, we take this byte OR. I'm going to use yellow for funct things. There we go. So now, if the value on this byte, or sorry, if the opcode is 0, the value on this byte wire over here is going to be exactly the value coming in on the funct pin. But if this is not 0, then this value is going to be whatever's on the funct pin plus 64, and then it won't trigger any of the byte constants. And so we can use this as a bit of a trick to make sure that we only recognize instructions that are R-type when we're actually looking at an R-type instruction. So now there are fewer of these, but there's still a bunch of them, so I'm going to grab... That was probably too many, I can hope. And use E to set all of those wires, and then set these ones manually. So, okay, going, let's see, maybe one by one, I'm not sure. So first over here is jump register. It's exactly like jump, except it takes the address from a register instead of from the address field of a J-type instruction. The next one is JALR, J-A-L-R, which is jump and link register. It behaves just like JAL, except it takes the address to jump to from a register. Also, it does not necessarily write the return address into register 31. You can pick a different return address if you like. This is an R-type instruction. If you'd like the return address to go into a different register, you just put that register in the RD field. The next instruction is add, which is just like add I, except not an immediate, as you would expect. Add U, same. Then there's also sub and sub U. Now you might notice sub and sub U don't have I-type versions. The reason that they don't have I-type versions is because you can do them with add I and add IU by passing a negative immediate value. And again, this is what sign extending is for, so we'll talk about that more later. So add's opcode is 33, add U's opcode is 32, I believe. Or, sorry, 34, yeah. Sub's opcode is 35, and sub U's opcode is... Oh, wait, hang on, something is wrong here. Sub's opcode should be 34. Eight, 9. This one is add. Ah, yeah, this one should be 32. I must have clicked the wrong one. Okay, that one's 33. This one's 34, so that should be sub. Yep. And then sub U gets 35. So, that. Okay. Then after sub U, we get logical AND, logical OR, logical XOR, logical NOR. Wow, I got exactly the right number. And then finally, we have set less than and set less than unsigned. SLTU like this. And so fix all their opcodes, or these are functs actually. So AND has funct 36, OR has funct 37, that. XOR has funct 38, NOR has funct 39, SLT has funct 42, and SLTU has 43. Perfect. Okay. So now we can recognize all of our instructions. So for example, if we have opcode 0 and funct, let's say 9, you can see the JALR line comes on over here. If I change the opcode to, let's say, 3, you can see the JALR line has turned off, but the JAL line has come on up here, the green one. So this is a good indication that this logic down here is working to prevent us from matching R-type instructions when we don't want to. Now there's one other thing, one other instruction type, which... What happened here? Interesting. There's one other instruction type which we're going to basically just treat separately because it doesn't actually affect the control signals basically at all, as long as we're well, yeah. So the instruction is NOP, no operation. And no operation is an R-type instruction with opcode 0 and funct also 0. And basically it's just not even a real instruction. It's just the instruction which is all zeros in the, like, the value of the instruction is 0. And sort of just coincidentally, in a full MIPS machine, the instruction that corresponds to, which I think is some kind of left shift, just doesn't do anything, right? It's a left shift of the value in the 0 register to the 0 register with a shift distance of 0. And so for now, we're going to identify it just as NOP, but we're going to ignore it. We're not really going to worry about it. The only reason that we want to identify it is because we're going to have one output on the bottom side of this decoder, one single bit output, which identifies whether or not we recognized the instruction. And if we didn't recognize the instruction, this output, which is called accept, is going to come on and say, hey, there's a problem, you're trying to execute an instruction that I don't know about. And so in order to check that, all we need is a big, basically multi-way OR gate. And the easiest way to make a big multi-way OR gate is to wire all these things together with buffers, like this. And so instead of just going one by one the whole way down, we can do the power of 2 thing. So I made 4 of them, and 8, and 16. And so this line that's coming out of the buffers, this line is always going to be on as long as the current instruction that we're looking at is one that we know about, right? So as long as any of the instruction lines are on, this line will be on. And so this way, even though we're going to ignore this NOP line other than this, if the operation is no operation, like this, you can see the accept pin still 1. Except, of course, we want to invert it. And so now you can see the accept pin is off. Okay, great. So now we're going to pull up our little list that we wrote a little bit earlier with the control signals. And we're going to start talking about how you can actually take these lines and use those to decode into individual control signals. So the first thing we're going to do is we're going to do the same thing that I just did with these wires. And, oh, oops. That. And we're going to use this just to give us a starting point, something to grab onto. You'll see in a second. So we want to extend all of these. There. These two. That, the yellow ones. Perfect. And in fact, if you see, what we want to do is we want to basically stretch these all the way across the whole component. Oh, yep, there we go. Some lag. All the way across. And I don't know if we're going to use this whole distance, but, you know, we might as well give it to ourselves. If we're working all the way over here, it's a little bit hard to figure out exactly which wire we're actually looking at. So to make that a little bit easier, instead of having all of these be green and all of these be yellow, I want to switch them. So we're going to have, let's say, alternating blue and turquoise on these lines. And that will just make it a little bit easier to make sure that we're actually looking at what we think we're looking at, because it'll prevent off by 1 errors, which are the most common ones. So just... actually, I don't like how those colors mix. Let's use purple. Yeah, that's better. If you want... Actually, does this look better? Yeah, that looks better. If you want a different mix of colors, of course, like, this doesn't matter at all. Use whatever colors you want. I would just recommend against having them all be the same color. And in fact, I think I said we were going to ignore this one. I'll leave it for now, but it shouldn't matter. So anyway, so the first control signal that we're going to have up here is RD source. And this controls the value of the destination register. Where are we going to write the result? Does it go to register 5? Does it go to register 2? Etc., things like that. And, sorry. The value of the register that we write to comes out of a different field of the instruction. It comes out of the RD field. But for I-type instructions, there is no RD field because the immediate overlaps where it would be. So instead, we take the destination from RT, or in the case of JALR, we're going to do something special, but that'll be handled elsewhere. So we need a way to identify when is it that we're supposed to use RT instead of RD. And in fact, the answer is, well, exactly when we have an I-type instruction. So how do we know that we have an I-type instruction? Well, it's because this value over here is 0. And so we sort of have a check for that already, but 0 check is cheap, and the not 0 check is free. So instead, we're just going to pull this up here. And so finally, we get this one last control line. And this one is true when we have an I-type instruction. And then for the sake of being simple, if this line is false, we'll say we have an R-type instruction. That ignores the J-type instructions, but that's fine because their control signals are very simple, and the uses for these wires aren't really going to overlap with them at all. So I guess we should extend these as well. And the question was, when should we turn on this RD source pin? When should we take the value from RT instead of RD? And the answer is exactly when we have an I-type instruction. So we'll just connect this. Nice and easy. And now I will grab this pair of wires and stretch them all the way over here. Okay. And so now we can really start getting into the control signals in earnest. Hopefully the next ones will be more interesting. Or not. So the next one is LUI. I already don't even remember what order I said earlier, so now I'm just reading off that list. Notice I'm making all these pins go up so that they're still readable over here. So LUI, what do? We match exactly that instruction and connect it to the pin. Very easy. Now the next one is write enable. So write enable controls writing back to the register file, not to the data memory. That's controlled by two different things, which we'll get to later on. And so when do we want to write back to the register file? Let's see. I have a pin out of the decoder that I already made, so I need to look at when this one comes on. It looks like we always want to write back for the instructions that we have over here, and again, we're just going to ignore NOP and the right thing will happen. So let's confirm that. The only exceptions are these four. So if it's any of these four instructions, jump, jump and link, branch equal, branch not equal, actually that's not quite right. Any of these four, but not jump and link, that one we do want to write enable because we want to write the return address. Or jump register down here, that one we don't want to write. If it's any of those four instructions, we don't want to write, otherwise we do. So what we're going to do is we're going to check if it is one of those four and then negate it. And so OR gates are big, and they take up a lot of space, and there's no four-way OR. So instead, we can do this detection using buffers like this. So we can detect jump, branch equal, branch not equal, and jump register down here. Now you might say, well, how come these branch instructions don't have link versions? Why is there no branch equal and link? The answer probably unsurprisingly, is that there actually is a branch equal and link instruction in the full MIPS instruction set, which you can basically use as a conditional function call. We're just not implementing it because it's not especially interesting. If you want to implement it, it's very easy to go out on your own and give that a shot. And that will be one of the extensions that I will propose once we're done with this whole thing. So the next pin is control type. This one's actually a little bit involved, so I think I'm going to skip this one for now and come back to it later. I'm thinking about it. Nah, let's do it now. I'm just going to give myself a little bit more space because this one actually needs a byte maker. There's quite a bit going on here. So there's a bunch of different control types that we can have. If you look back at the machine diagram over here, excuse me, hopefully the slideshow is open correctly. I know sometimes when I record it doesn't. It looks like it did. If we look over here at control type, you can see there's 4 values going into the multiplexer, and we'll talk about what these 4 things are later when we're assembling the whole machine. But control type needs to have, at least 2 values for controlling this multiplexer. The other thing that you can see is that control type is coming out of here, and there's this 0 input to the MIPS instruction decoder that we don't have. And 0 is one of the ALU flags that we built on to the ALU. But the problem is, because the ALU is controlled by ALU op, a signal coming out of the decoder, if the 0 flag comes into the decoder from the ALU, we're going to have a cycle, and Turing Complete won't like that. And actually, in this case, even though there wouldn't be a cycle if we built the decoder inline, because the 0 flag isn't going to affect the ALU op, in this case, Turing Complete's restriction is actually going to force us to do something good. So in this case, Turing Complete's restriction is going to force us to move the branching logic. The 0 flag is used to decide if we should take the conditional branches. This is going to force us to move the branching logic into a different conditional unit, which we'll put up here. And I think that's actually a good thing. It's more extensible for one, and it'll help us when we get to pipelining. So instead of just outputting the 2 control bits for that multiplexer, we're instead going to output 5 bits with information about... Is it 5? Yeah. We're going to output 5 bits with information about what the control unit needs to look at to decide what to do. So the first bit of that is super easy. We want the first bit to be on if we have a jump instruction. Just a regular, plain old jump to the value. And that is only on for the jump instruction. I don't know why I put 2 buffers here. Actually, I don't know why I put a buffer at all. Okay. And that's going to go to pin 2, just for consistency with what I have. Actually, I guess that's why I put buffers, because the thing in pin 1 is the more involved one. So this one is going to be on if we have a link instruction, an instruction that requires us to link the value of the next instruction, the address of the next instruction, into the return address register. So we have that for jump and link, and we have that down here for jump and link register. And of course, to keep your things neat, you should always try and make sure that these lines are straight. This goes to the first bit. So this first bit says that we should link. Alright. Now the next bit says that we should jump to the value in a register as opposed to jumping to the address coming out of the register file. As opposed to the address coming directly out of the instruction, we should jump to the address coming out of the register file. So this is true for jump register and jump and link register. So, in fact, if I drag from the buffer, that works a little bit easier. So in these cases, we want to jump to the value in a register. All right. And then the last two pins are the different types of branches. So in this case, we have branch equal, branch if the 0 flag is set, because we're going to do the comparison with the subtraction, and branch not equal, branch if the 0 flag is not set. And this is all the values that control type can take. And in fact, this took up less space than I thought it would, so we can actually move all of this over onto one pin. So let's put that over there, that should fit. And then I can just take these and there we go. Alright, perfect. Now this pin gets its own space. Alright, cool. So that's the control type, and the decoder is going, the control unit is going to figure out what that means somewhere else. Alright. The next one is the ALU source. This one is actually definitely going to be bigger, so I should give myself more space for this. Alright. Oh, except, I guess I do want it to be here. Yeah, okay. We just might use the one next to this as well. That's okay. Sorry, ALU source or ALU operation? Ah, yeah, okay, this is ALU source, so actually this is just one bit. Is that true? Why do I feel like that's not right? Yeah, because it's not. Okay. Okay. So the reason that this is not a single bit is because there are 3 possible values that might need to go into the second argument of the ALU. There's the value coming out of the register file, there's the direct value of the immediate, and there's the sign extended value of the immediate. So all we need to do is figure out when we should use which one. So, looking at the pinout of the decoder that I already have, it looks like I used a byte maker. I guess there's not enough space to do that. Not very happy with this though. Let's see. I think I'm going to leave myself this box as working space. And, actually, I guess what I can do is we can move all of these pins up like that. So make our decoder take up one more row of space, and then that way we have this row for just whatever logic we need to fit wherever it has to go. That should be a bit nicer. Okay. So this pin is the second ALU source. We only care about these 2 bits. The top bit is going to be the most common case. It'll usually be on. And the second bit is going to usually be off. So the second bit is going to control whether we want the signed immediate or the unsigned immediate, and this bit is going to control whether we want an immediate at all. So the only case where we want an unsigned immediate, actually, perhaps surprisingly, is the immediate mode logic operations, these 3. And that might be, a little bit surprising. Why would it only be in these 3 cases and not in, say, I don't know, set less than unsigned? And the reason is that set less than treats the comparison as an unsigned comparison. So if you have if you give it a negative argument, it'll treat it as though it's a very large positive unsigned number. But it doesn't treat the immediate as an unsigned value for whatever reason. And so actually the only time when we should treat the immediate as an unsigned value is when we're doing logic like this. And so in order to detect that we're doing that kind of logic, we can just use a buffer, like we have been. There they are. And attach them to the immediate type logic instructions. And I paused for a second there because this actually wasn't the way that I did it in the one that I already built, and I was trying to figure out why I would have done it the way I did it, and the answer was that I was being dumb. So everybody makes mistakes. It really helps to go into these kinds of things with a plan, because these circuits are not small, of course, and they can get pretty annoying. So doing it this way lets us push that complexity off somewhere else. If you wanted to try and make a more score-efficient decoder, you could probably do that pretty easily. Of course, the delay is great, because this is basically a lookup table, but the NAND is not good. Okay. And so then the top bit controls whether or not we want an immediate at all, and the answer is, let's see, we always want an immediate for I-type instructions. We never want an immediate for R-type instructions. With the exceptions of branch and branch not equal. So branch and branch not equal are a little bit weird. Despite being I-type instructions, they need to compare two values in registers. So they need the ALU source to take its value from a register, and they'll send the immediate somewhere else to compute the address that we should jump to. So I just gave myself a little bit more space because I'm going to need to fit a NOT gate. This is going to be one of those check it and then do the opposite things. Come on. Grab it like that. Ooh, it like just barely doesn't fit? Okay. I can do it like this. That works. Okay. Right. So here, we're going to want to always take from ALU source. Okay. Sorry. So we're going to want to always take from a register. Wait. No. Okay. I'm confusing myself. The NOT means that this is enabled by default. Enabling this makes us take from an immediate. So we're going to always enable this, except when the instruction is R-type. So take from this wire. Or when the instruction is I-type, but it is branch equal or branch not equal, which are these two wires right here. So that's the take immediate pin. Okay, cool. Hopefully I'm done confusing myself like that, except I know that that's not the case because the next pin is the worst one. So this is the ALU operation. This is, if you want to try and be smarter about instruction decoding, you want to try and find relevant bit patterns to control what you should do, this is probably the pin that you should start looking at. I think there's the most patterns over here, and there are also probably the most interesting patterns. But we've already talked actually about what these different pins mean when we were building the ALUs. So if you remember, whenever this wire is on, it means we're doing logic. And the check for that is going to be a little bit more involved than this, so we can't reuse it. But whenever this pin is on, it means that logic is happening. And in fact, I can give myself a lot more space since this byte maker fits into one box. So this pin means logic. This pin means that the operation that we're doing is not and or. And that means we're doing addition, subtraction, XOR, or NOR. And then this pin means we're doing subtraction, XOR, or OR. And in fact, all of those things are very independently checkable because we have all of the instructions out on simple wires like this already. So the first thing that I want to do is I just want to combine the immediate mode operations with their non-immediate siblings, just because it makes... Oop, I did not want that to be attached there. I'm going to have to undo that, which is going to make the game just pause. Nope. Come on. There we go. Okay. And the reason that I want to do this is because the ALU operation doesn't care whether or not we're doing an immediate mode operation, so this will just make the rest of the checking easier. So we're going to start. I'm just going to go in order, so we're going to take add I. And of course, it doesn't care whether or not it's signed either, so in fact, this is going to be four-way. So we're going to have add IU, well, add I and add IU. This one is add, and then the one under that is add U. And if we wanted to care about the difference between signed and unsigned arithmetic, we would have a different circuit for detecting overflow errors, which is the difference between them. And we would output the signed pin and use that to detect errors. Okay, so this one's addition. The next one that has immediate mode and non-immediate mode is AND. Did I not? Oh, actually, we might end up not looking at these. Oops, okay, well, whatever. So the next one is AND. So we have AND I, and then we have non-immediate AND down here. Then OR. So that one's also pink. And non-immediate OR. And then XOR. Also blue. Not that wire. It's on this one. And non-immediate XOR. Alright, there we go. So that's all the wires that we need to look at. And then sub, we actually do care about looking at this one, so we're going to have the sub line over here, and the one below it is unsigned sub. Okay, and then I don't think we need these, but I'm going to leave them for now just in case. Alright, so, and then I'm going to have to bring up the NOR line as well. So I can comment these to say what each of these mean. This one means addition. Nope, definitely don't comment that wire. Okay, I should have dragged that away instead of undoing. This one is AND. This one is OR. And of course those are facing opposite directions. I would really like for that to be fixed. It's pretty annoying. And this one is XOR. And then this one is subtraction. Why did it leave comment mode? Okay, and then the logic is just exactly what I said earlier. So this pin on the left is on whenever we're doing... how do I want to do this? Yeah, that should be fine. Whenever we're doing sub, XOR, or OR. So I'm not going to worry too much about keeping this part clean. So we're going to have sub, XOR, or, and those weren't in the order that I just said. That's fine. This next bit is on whenever we're not doing and or. So we have and or on a line like this, and I think a NOR gate will fit here, which is bigger than buffers and a NOT gate. I just don't want to think about it. Want to keep that comment legible. Like this. And then this final pin is on whenever we're doing logic. So and, or, XOR, or NOR, which I'll have to pull in from below. So, okay. And, or, we'll put NOR on that one, and XOR goes over here. Down. Oh, this is going to be a little bit awkward, actually. Okay, that's better. Like I said, I'm not too worried about keeping this neat. If you want this to be neater, I'm sure it would be very easy to build yours cleaner than this. I'm just sort of rushing it because I don't want the video to get too long, and it's already quite long. But thankfully this is the hardest pin to get right. And so here I'm just bringing up the NOR wire, and of course I brought it up from the wrong place. Gotta move that over, like this. Alright, there we go. So now this wire is on whenever we're doing logic. So just to check that quickly, let's change the operation to be and I, which means we want this input to be 12. And it looks like logic came on, and yeah, 4 is the correct ALU control for that. And as I suspected, we did not actually use the add pin. So oops. Anyway, not going to waste too much time trying to correct that. And in fact, I'm not even going to try and fit a pin in this box, even though I think the next one is also very simple. I'm just going to give us some more space to try and help keep it just a little bit neat. Maybe pretend just a little bit like I care. So this one is mem_read, and this pin should come on whenever we're doing a memory read operation. If you remember from just a little bit ago, we only have 3 of those. We have load byte, we have load byte unsigned, and we have load word. And so if you check, those are here, load byte, load word, load byte unsigned. They're all right next to each other, which is very nice. So here's load byte unsigned, and load word. So that pin will come on whenever we're reading memory. The rest of them should be like similarly simple. ALU op is the worst one, and it's not close. Okay, this one is SLT. This one comes on whenever we're doing a set less than operation, and we have 4 of those. We have set less than unsigned, set less than immediate, and set less than unsigned immediate. Or actually, I guess it's immediate unsigned, but whatever. So zoom out to find the right wires. It looks like this one and the next one are the immediate modes. Like that. And then looking down here at the bottom, this one and the next one are the non-immediate modes. I'm gonna move that over. Like that. Okay. So that gives us our set less than control. And I'll go back through this just to double check and make sure that I actually connected the things the way that I meant to. But I should notice pretty quickly if I say something that's wrong. So if you think that something that I say for the value of a control pin is wrong, you should go look at the data path. Think to yourself, would that make the wrong thing happen? The data path is what we call that diagram, the logic diagram of the whole machine. And if you think that that's wrong, then you should leave a comment, and I will hopefully be able to fix the mistake that you have found, because I am sure that I am going to make at least one. Okay, so this pin is the word write enable. We just call that word we for some reason. That's like a standard abbreviation. At any rate, that only comes on for a single instruction. There's a store word instruction. That's the only thing that can write a word to data memory. These pins control data memory. However, this pin has a brother, or a sister, whatever you like, which is byte write enable. This one comes on for store byte, of which there is also only one. So you might notice there's load byte and load byte unsigned instructions, but there's no store byte unsigned instruction. The reason is because the difference between load byte and load byte unsigned is about the top 3 bytes of the whole 32-bit word that you load, because registers have 32 bits even if the byte only has 8. When you're storing a byte, you're only touching 8 bits of memory, and so the top 3 bytes don't matter, and there is no distinction between being signed or unsigned. So that's just completely controlled by whether or not we're doing a store byte, and in fact, I did just make a mistake. that is the load word line. There you go. That one should go over there. Okay. The next control is byte load, and as I just discussed, this one actually does have two cases. So here we want to make sure that we get... Why did I put an underscore? We want to make sure that we get this one in both the signed and unsigned case. So we'll put it like that, and I think these ones have the same color because they're separated by load word. Yeah. So these ones are blue. That is XOR I. This one is load byte. That one is load byte unsigned. Alright, great. And you can see at the bottom the pins are becoming illegible, so hopefully something will be done about that soon. I know people have been talking about it in Discord. Alright, and we're almost done. So the last pin is signed. And so this controls whether we want to do the signed or unsigned version of an operation, which, as I mentioned, we're only actually going to care about this for comparisons and for load byte. And we're not going to worry about the difference between add and addu, for example. So I just want to make sure that I get this circuit correct, so I'm looking at my pinout. Looks like in the other version that I did, I actually did care about the difference, but I'm not going to worry about it here. It takes up a bunch of space. This has gone on long enough. It's easy to change if you want to change it for your own purposes. So the only thing that we should care about here is the difference between SLT and SLT IU. The difference between... Oh, I see. I took this picture before I fixed the bug. Okay. So which operation is signed? SLTI is signed, SLTIU is not. Then there's also SLT, which is signed, and SLTU, which is not. So one of these will be for SLTI, one of them for SLT. And then this last pin is just for load byte, which will of course be signed. And we just used that over here. I think it's this wire. That one. Alright. And then we have SLTI on this wire. And SLT on this pink one down here. Ooh. Yeah, alright, there we go. Alright. And that's the signed flag. And so you can see there's actually like a whole bunch of wires here that we actually never looked at. And that checks out, so we can actually check pretty easily which ones did we look at. So if we hover over this wire, or I don't know, let's pick a random wire that I think maybe I didn't touch. Let's say this one. I want to check, did I actually touch this wire? I can hover over it with a different color and press E. And you see this one actually came on, so I did touch this wire. And then to undo that, I'm just going to reselect pink and press E again. And so you can do that to check which wires we actually did and didn't touch. There's going to be several that we didn't touch. In particular, add and addu, I don't think we actually used either of those. I know we put them into these buffers, but I don't think we actually used them. And that's fine. There's really no penalty to matching a case that we then never look at, except the NAND scores. So you could delete the ones that you don't use, or you could always just leave them, and then if you decide to extend the machine later in a way that matters. Oh yeah, I guess pressing E does have this side effect. If you decide to extend them later, you'll just have those wires there, and you'll be able to use them easily. Or, I don't know, if you care about the NAND, maybe you just delete the equality check itself, which is the only part that affects the score. It's easy to add that back. So one other thing that I see looking at this is there's a lot of empty space on this thing, which I personally don't like. So just to remind you how useful copy-pasting is, and just to show how easily you can fill all that space. Buffers are free, and all of the data that we have in this decoder is flowing to the right on these wires, right? So putting buffers here literally cannot have an adverse effect. And I think I grabbed a little bit more than I meant to there. So let's grab these buffers. And so we're going to, and you can see the bottom here, as we put these buffers down, it's filling in the empty space in the component. In fact, this is actually more buffers than we need. So I can go through and make sure that I've only left one in every box, and then fix all the wires. So let's see, I'll leave that one. Looks like I only needed every third one, so oops on that. I actually did want to leave that one. Yeah, I didn't want to leave these. Okay. Yeah. Oops. That's taking me longer than I intended it to, because this was just supposed to be a simple example of using copy paste. Alright. And in fact, I don't need either of those. I'm going to add one more buffer up here. Okay, and then I can fix all of that carnage by just grabbing this whole wire. Not the buffers though. Just these. And dragging them over. Okay, and then I guess I have to fix these wires individually. Oh, no, definitely don't do that. I hit undo, and now the game is frozen. Okay, and anyway, the point of that was just to demonstrate using copy and paste. The next step was going to be to copy and paste these actual buffers into every column of boxes somewhere where they fit, just to try and take up space. I guess this has gone on long enough now, and I don't need to make more mistakes that make me waste a lot of time talking about stuff like this. I think you can get the idea, and I'll just fix up all these connections quickly. But yeah, this is the easiest way, I think, to build an instruction decoder. It doesn't require a whole lot of brain power. You just have to check and try and make sure that you actually are checking the cases that you want to check, and getting the right wires. Alternating colors helps with that. There is one way that can sometimes be easier. I think it wouldn't have been easier just because of this sort of 2-pin thing that MIPS is doing. But what you can do, if I can find it, is it normally in I/O? No? Huh. Oh, maybe you can't put ROMs inside of custom components. I guess that would make sense. Okay, well then I guess it won't work, but you could do it with a file ROM. So what you can do is you can put a lookup table in some format that you can then interpret, bits for bits, in a file somewhere. Take a file ROM, point the file ROM at that lookup table, and then split it with a 64-bit splitter and as many byte splitters as you need. In our case, I think we have 20 pins, so you would need 3 of these. And you would connect the byte splitters to the different byte wires, and then you set up your lookup table so that if you pass the inputs as an address to the lookup table, these top 20 bits, so these ones all the way up through this one, these would just be your output values. And this is like the easiest way to build the circuit. Building the lookup table can be a problem in this particular case because of the fact that you need the opcode detection to work no matter what the value of the funct is. Doing this would be a little bit trickier. Not impossible, but a little bit trickier. I don't think that way of doing it is particularly interesting, so I'm not going to talk about it any more than that, but it's a good thing to be aware of that it's possible, and it's also, like, super cheap, right? Because the file ROM does not cost anything, so it's, like, actually free. Oh, wait, no, that's not true. It looks like it has the same cost as a regular ROM. I did not know that. It doesn't say that in the corner. I will go report that as a bug. At any rate, it's still a very easy way to do it. So yeah, this is going to be the instruction decoder that we are going to use for MIPS. I will clean up the circuit a little bit, although I don't think we're going to have to look at it again. And I think this video has gone on long enough, so next time we will talk about sign extension and that kind of thing in the control unit, and I will see you then. Thank you very much. As a reminder, this is what we're going for.